Hello, my name is Brett Parrish, and I'm going to be talking to you about my conceptual design review for my project Greenhouse Automation. In this presentation, I'm going to cover the objective, requirements, performance specifications, concept of operations, design alternatives, and the feasibility of design. The objective is to design an affordable, self-sustaining greenhouse system that will adjust variables to simulate proper growing conditions within the greenhouse. These variables will consist of air temperature, soil moisture, humidity, and lighting. Gardens are time-consuming because they require attention and effort. So what is the problem that is trying to be solved? Design an automated system to make gardening convenient and easy. Some requirements for this project are: it needs to be affordable, around $500 to $1,000. It needs to use programmable logic to decipher inputs and outputs. It also needs to be self-sustaining so it can maintain the proper growing conditions. And last, it needs to meet the National Electrical Handbook standards. There are four main performance specifications for this project. Number one, the display on the control panel needs to show the correct data readings. A comparison between data readings and actual measurements will test the accuracy. In order to test these actual measurements, a thermometer will be used for the air and soil temperature, a hygrometer will measure the humidity, and a visual measurement to verify that the light turns on. Number two, the system will need to maintain air temperature between 75 degrees and 90 degrees. The soil temperature needs to stay between 60 degrees Fahrenheit and 70 degrees Fahrenheit. The humidity percentage will stay between 80 and 90%. The soil moisture percentage will stay between 35 and 40%. The water level in the misting station will be between 10% and 90%. And last, a cycle of light for 12 hours on and 12 hours off. Third, an alert will be sent to the phone if a threshold is exceeded by 5%. For example, if the air temperature reaches 95 degrees, an alert will be sent. The last specification is the greenhouse layout. It will be 4 feet by 4 feet by 5 feet tall and will hold up to 6 plants. CONOPS, or concept of operation, defines the characteristics of the desired end product and describes how requirements will be employed to achieve desired objectives. In this section, I will talk about the logic, greenhouse layout, and the 5 controlled systems, and how these characteristics play a part in an automated greenhouse project. This is the brain of the whole system. It tells outputs to turn off and on based off of data from the inputs. An Arduino board is a programmable microcontroller that controls inputs and outputs. It uses C++ as its main language. The picture on the bottom right demonstrates an Arduino Uno 3 board. For the control panel, the control panel door will consist of one display screen, 7 LED indicators, and 1 emergency stop. Inside the panel will be the Arduino board, terminals, and relays. In this picture is the layout of the front door. One is the display monitor that will show the data being obtained from the greenhouse. Number 2 is an indicator that pump 1 is in motion. Number 3, another indicator that pump 2 is on. Number 4, humidifier indicator. Number 5, heaters indicator. Number 6, the heating pads for the soil temperature is on. The lighting indicator number 7 is on when the lights are on. In indicator number 8, the fans are used to decrease the humidity. Number 9 is an emergency stop in case something goes wrong and needs to shut the whole system down. For the greenhouse, it will be purchased so that money is saved and is more efficient. The dimensions and material. It will be 4 feet by 4 feet by 5 feet tall and will be constructed from plastic. In this drawing shows the layout of the greenhouse. It is 4 feet wide, 4 feet long, and 5 feet tall. There are 2 types of temperatures that will be monitored and controlled. The first is the air temperature. Temperature sensors will be used to communicate with the Arduino board, and from the Arduino board outputs, it will activate and deactivate heaters when the input air temperature exceeds a certain threshold. This is very similar to how the soil temperature will work, except there will be a temperature probe in the soil, and heating pads will be used to heat the soil. To control the humidity, a humidity sensor will be placed in the center of the greenhouse. The sensor will read 0 to 100% in relation to the humidity. Fans will turn on and off according to the reading in the humidity sensor. 2 fans will be used to regulate humidity. One that sucks new air in and one that blows old air out. The picture in the bottom right shows the humidity sensor that is used for the Arduino board. It can also do temperature. To assure that the plants get the right amount of water, a moisture sensor is placed within the soil. From here, it will communicate with the Arduino board to turn off and on the mister pumps. The sensor will have a reading from 0 to 100% according to the moisture of the soil. Using this reading, when it is below 10%, the misters will supply water. Once the moisture reaches 45%, the pumps cut off, therefore stopping the water process. The water system consists of 2 stations, the water storage station and the misting station. To make the system fully self-sustainable, it will need to have a water source. To do this, rainwater will be collected into a 55-gallon drum from rain gutters. In the misting station, there are 2 pumps. Pump 1 transports water from the storage to the misting station, and Pump 2 from the misting station to the soil. A sensor in the misting station monitors the level of water, and when the level gets low, Pump 1 turns on, which demonstrates the water process. The red circle represents Pump 1 and is located in the water storage station. Pump 2 is represented as the green circle, which is in the misting station. The purple circle shows the sensor that is used to measure the water level. A programmable schedule will be set to cycle the lights 12 hours on and 12 hours off. The lighting layout will consist of 5 T8 fluorescent bulbs. This will provide an equal amount of light for each of the 6 plants. When evaluating the automated greenhouse, there were alternative designs. The final design was decided by using decision matrix to choose the best approach. In the next set of slides, I will talk about 6 alternative designs and the reasoning behind the final decision. PLC versus Arduino, greenhouse construction, sensor placement, water source, front panel layout, and lighting system. Using a numeric rating, 4 being the best and 1 being the worst, different approaches were rating on certain specifications. In this slide, I will talk about PLC versus Arduino. The cost of the PLC is rather high, so I gave it a rating of 2. And the Arduino is not nearly as expensive, so I gave it a rating of 4. The cost of components such as relays or sensors For the PLC, were really high, and for the Arduino, were very cheap. The complexity, the PLC is a lot easier to wire up. It doesn't require resistors, and Arduino requires pull-up resistors, different terminations. When talking about the development of these two things, the PLC uses ladder logic, which is easier. Arduino uses programming in C++ language, which requires a little bit more effort. Totaling these values, PLC had a total of 9 and Arduino of 11. So 11 being higher, the Arduino was chosen for this project. Greenhouse construction, buy versus build. The cost to buy one is about $100. So I gave it a price of 4. To build one is estimated to be about $120 to $150. The complexity of buying one is very easy, just put it together. Versus building it, you'd have to spec out parts, construct it. The efficiency when buying one is going to be high because there's not going to be less room for error. Versus building it, it may not meet standards, may have holes in it which will leak heat. The total for buying was 12 and the total for building was 6. So for this design, a greenhouse will be bought. Sensor placement. To use multiple sensors or to just use one. The cost for multiple sensors got a rating of 2 because it would require more money, versus the single sensor would require less money. Programming multiple sensors to work with one another could be pretty complex versus just having one single sensor activate and output. The development for multiple sensors is a 2 because the programming would be hard versus just using one sensor. For the accuracy, multiple sensors would be more accurate because it would give you several different readings spread out through the greenhouse, as to a single sensor is limited to a certain confined space. The total for the multiple sensors is 9 and the total for single is 14. So single sensor setup will be used for this design. Water source, using hose water versus rain barrel. Cost for the rain barrel would be less than the hose water. Complexity, the rain barrel would be easier to set up. Development, they're about the same because they require the same amount of programming. The efficiency got a high rating for the rain barrel because it is recycling rainwater. For the total, hose water had a rating of 9 and rain barrel 14. So the rain barrel design will be used for this system. Lighting. To use LED lighting or fluorescent bulbs. The deciding factor for this was the cost. Fluorescent bulbs are a lot cheaper than LED lights. So the total for LED was 9 and 12 for fluorescent. So the fluorescent will be used. The layout of the front panel. To use multiple meters or just one single meter. The cost of multiple meters could get rather expensive, so I got a rating of 2 versus just one single meter. The complexity. There would be several wires using multiple meters, so I got a rating of 2 versus just one single meter. The development. Programming multiple wires and inputs could be difficult versus having just a few wires programmed for the single meter. The total value for the multiple meter was 5 and the total for the single meter was 10, so it will be used. The design of the automated greenhouse is feasible. It will require organization and method planning, but can be built and designed for a budget between $500 and $1,000.
You can use C++ language and will be self-sustainable.